Good morning. Today we will start the new chapter, that is energy transfer in turbo machine. Okay. In this chapter, mainly we discuss kinematic and dynamic factors of the turbo machines. Okay. Here, the kinematic factors means which will be related to the movements like velocity, acceleration. Dynamic factors means the forces which are causes the movements, that is velocity or acceleration. Okay, these factors we discuss in this chapter, that is related to turbo machine. Okay, in this first we will derive an important equation, that is Euler's turbine equation, which will be useful in calculating the energy transfer of different turbo machines. Okay, so here to derive the Euler's turbine equation, we have considered a generalized rotor here, generalized rotor. Okay, see here the absolute velocity v1, which enters the rotor at inner radius r1 and leaves the rotor at outer radius r2. Okay, and the O1 is the axis of rotation of the rotor, and the rotor is revolving with the angular velocity of omega. Okay, see to derive the Euler's turbine equation, we will consider certain assumptions here. Okay, those assumptions are: the fluid flow through the turbo machine is steady, mass flow rate is constant throughout the rotor, steady state of fluid does not vary with time, rate of energy transfer is constant, and leakage losses are neglected. Okay, these are the assumptions we made to derive the Euler's turbine equation. Okay, see whatever the absolute velocity which is striking the rotor, which is at certain angle to all the three principal axes x, y, z. Okay, suppose let it be this is the axis. Okay, whichever whatever the absolute velocity which is striking the rotor, which is at certain angle to the all the three axes. Okay, that is x, y, and z. Okay, this absolute velocity will be resolved into three velocity components. Okay, those velocity components are like this: axial velocity component VA, radial velocity component VM, tangential velocity component V. Okay, the axial velocity component means which is in the direction of the axis. Okay, suppose this is the rotor, this is the axis. Okay, the VA will be resolved in the direction of axis, in the direction of axis. Okay, next we have the radial velocity component, which is in the direction of the radius of the rotor are perpendicular to the axis, like this. This is the VM, this is the VA. Okay, one more, the tangential velocity component VU, which is resolved in the direction of tangent to the radius of the rotor, like this. Okay, these are the three directions of these velocity components, that is VA, axial velocity component, VM, radial velocity component, VU, tangential velocity component. Okay, see to derive, before derive the Euler's turbine equation, first we should know out of these three velocity component, which velocity component will cause us the tangential movement of the rotor. Okay, you just see here the VA. Okay, the VA, that is axial velocity component, which causes the axial movement of the rotor. Okay, the radial velocity component, this just causes the radial movement of the rotor. Okay, but the VU, which causes the tangential movement of the rotor, like this. Okay, so we need to consider the tangential velocity component VU in deriving the Euler's turbine equation. Why means the tangential velocity component will causes the rotation or tangential movement of the rotor. Okay, that's why we will consider the VU, tangential velocity component, to derive the Euler's turbine equation. Okay, see the Euler's turbine equation is derived based on the second law of Newton's second law of motion. So what is the Newton's second law of motion? Force applied on the rotor is equal to rate of change of momentum. Okay, or the rate of change of momentum is nothing but mass into change in velocity per time. Okay, say the force applied on the rotor, that is F. Okay, the mass of the fluid is M. Change in velocity. Here, which velocity component we need to consider out of these three?
Tangential.
The tangential velocity component we need to consider, because that will cause us the tangential movement of the rotor. Okay, so change in tangential velocity component divided by time. Okay, or this equation you can write it as m by t delta v. Okay, see here m by t, the mass flow rate per time. Okay, that can be represented as m dot. Okay, this is mass flow rate of the fluid per unit time. Okay, delta vu can be written as vu1 minus vu. Okay, this is the force, tangential force applied on the rotor. Okay, or the torque applied on the rotor can be defined as force into radius. Force applied on the rotor into radius of the rotor. Okay, that is torque F into R. What is the force? Here we have m dot. See here into R. R means we have the two radius. One is the absolute velocity which is entering the rotor at inner radius R1, and the absolute velocity which is leaving the rotor at outer radius R2. Okay. So here the V1 means that is the tangential velocity at the inlet. V2 is the tangential velocity at the outlet. Okay. So the inner radius R1 should be multiplied with VU1.
R1 minus V2 into R2.
And outlet radius R2 should be multiplied with VU. Okay, this is the torque applied on the rotor. Okay, next we have the energy, rate of energy transfer. Represented by E over dot. Energy transfer will be written as torque into angular velocity. Torque into angular velocity. Then what is energy transfer? Rate of energy transfer, that is torque into angular velocity is omega. Okay. Then the energy transfer. What is the torque here? Torque equation m dot vu1 r1 into omega 1 minus vu2 r2 into omega 2. Okay, this is r we can write, but tangential velocity of rotor, that is u, will be written as angular velocity into radius. Okay, the tangential velocity of rotor u will be the product of angular velocity into radius. Okay, so here whatever the radius and angular velocity is there, in place of that we will write the tangential velocity of the rotor. Okay, that is m dot vu1 u1. U1 means tangential velocity of the rotor at inlet. In place of r2 omega 2 we will write u2. This is the tangential velocity of rotor at outlet. Okay, this is the Euler's turbine equation. So here, this is the Euler's turbine equation per unit time. Okay. Now we need to convert this Euler's turbine equation, that is energy transfer equation, per unit mass. Okay. Energy transfer per unit mass flow of fluid, that is represented by small letter e. Okay, that is whatever the rate of energy transfer is there, that is energy transfer per unit time, that is divided by mass flow rate, that is m dot. Okay, then if you divide this equation throughout by m dot, what you are going to get? VU1 into U1 minus VU2 into U2. Okay. Then the energy transfer per unit mass flow rate, E is equal to VU1 U1 minus VU2 U2. Okay. This is the Euler's turbine equation. Per unit mass of fluid. Okay. See this Euler's turbine equation. Now we need to write it for power generating turbo machine and for power absorbing turbo machine. Okay. This for power generating turbo machine. Okay. See here. See what is the definition of power generating turbo machine? What is the definition of power generating turbo machine?
Fluid energy is converted.
Here the fluid energy is converting into mechanical energy. Okay. Say the fluid energy is converting into mechanical work means here the fluid energy at the inlet is greater than the fluid energy at the outlet. Okay. See here whatever these terms are there, U1, U1, VU2, U2. Okay, this is the fluid energy at the inlet of the rotor and this is the fluid energy at the outlet of the rotor. So, for power generating turbo machine, the fluid energy at the inlet VU1, U1 is greater than VU2, U2 and energy transfer is positive. Okay, for power generating turbo machine, VU1, U1 should be greater than VU2, U2 and E should be positive. Okay. So the Euler's turbine equation for power generating turbo machine is VU1 U1 minus VU2 U2. This is the Euler's turbine equation for power generating turbo machine. Okay. Similarly, Euler's turbine equation for power absorbing turbo machine. What is the definition of power absorbing turbo machine? Here, the mechanical work is converting into fluid energy. That means in power absorbing turbo machine, the outlet fluid energy, the fluid energy at the outlet is greater than the fluid energy at the inlet. That means here the VU2, U2 should be greater than VU1, U1 and E is negative. That is energy transfer is negative. That means work is applied on the machine, applied on the rotor. Okay. So then what about the Euler's turbine equation for power absorbing turbo machine? E is equal to VU2 U2 minus VU1 U1. Okay. That means the Euler's turbine equation for power generating turbo machine is E is equal to VU1 U1 minus VU2 U2. Euler's turbine equation for power minus V1 Q1.